Hi, so our project is remotely piloted vehicles,
I'm Daniel.
I'm Dhruv.
and I'm Nandini. So remotely piloted vehicles has already been explored, but we wanted to focus particularly on using solely an internet connection to do so. And this way, it would be something that's more accessible to everyone. So we developed software for remotely piloted vehicles, and we use additional sensing through camera feedback as well as range sensors. And our final goal was to evaluate the strengths and weaknesses of remotely piloted interfaces. We had two different vehicles, and they had different hardware and software components, which we will get into.
So starting off with the hardware, our first vehicle features rear-wheel drive and front wheels that rotate, meaning that it drives similarly to a normal car that you would see on the street or on the highway. And initially, this vehicle had an ultrasonic sensor on the front that would rotate using a servo, but for our purposes, we replaced it with a USB camera so that we could provide live visual feedback to the driver. And as you can see on the video on the right, the camera rotates in conjunction with the wheels so that you're always facing the direction that you're turning in. And then for our second vehicle, it features a stationary USB camera, and it uses a drivetrain called Mechanism Drive. Mechanism Drive allows for omnidirectional movement, which means that it can move in virtually any direction, such as forward, backwards, strafing left and right, as well as moving diagonally. And we initially hypothesized that this type of movement would allow for more streamlined maneuverability and also allow the driver to better navigate around tight spaces. Both vehicles use the Osoyu Model X motor drivers, which have three variables that correspond to each motor. And by controlling those variables, we can control the direction and speed of each of the motors.
So now moving on to the networking, this allowed us to create that remote connection we were talking about. So to look at the network architecture in the most simplest terms, here is the server, which is essentially the robot and the Raspberry Pi that's on each of the robots. And then the client would be any PC or laptop that you're using to connect with. And in the middle is our VPN zero tier, which allows for a direct or peer-to-peer connection to occur. So the camera data is sent from the server to the client, and on the other hand, the movement commands are sent from the client to the server. And this direct connection we have allows it so that even if the robot and the client are on two different networks, they're still able to communicate with each other. So this is zero tier, which is the VPN client that we used. So essentially, this allows you to create a virtual local area network. So if your robot is on a Wi-Fi in this facility and your client is on a Wi-Fi in a different facility, they would still be able to communicate with each other because it's on the same virtual private network. So over here, you can see that the physical IPs are all the same because this is based off of your Wi-Fi connection. And then there's your managed IPs, which zero tier assigns within a specific range. And below that are the managed routes. So first is your local area network. So this would be if both devices were on the same network. And then if you were trying to connect with two different networks, you would use your default gateway to route it. And this basically just passes the traffic through. We tested it and we were able to get it to work with the robot at this facility driving and someone controlling it from their house miles away.
So now we're going to talk about some of the car software for both the Mechanism and Ackerman steering. So we had two main scripts running. We have the camera script, which basically gives the camera stream that you can see on the client side. And we also have the server code. So that receives commands from the client, which is an app that we made. And this is just basically to move it forward and backward and sideways. And we also have a variables, which just maintains the port and IP we want to operate on. So this is our camera feed. And the way this works is we use OpenCV to capture the frames, and we use JPEG compression to send it over and create a stream. So currently, this works well over the local area network, but sometimes in poor network conditions, some frames will drop and the quality will go down. So we're also looking into improving compression and encoding. So this is another feature we want to implement at emergency stop. So to experiment with different sensors and see how they can benefit the driver. So basically, the way this works, if you have this on, whenever it's about to crash or it goes into like a wall, it'll stop. And so we're using a distance sensor, and this checks like 1,000 times a second to see if it's in range or not. So And we also have a switch in the client to turn this feature on and off.
So now moving into the client software, this basically allows for easy usability for the driver. So over here is our Mechanim UI. We used React as our framework to build the app. So this allowed us to use like JavaScript, HTML, and CSS. And we used Ant Design for the components. And then Python was our backend, as you mentioned, with the server. So over here, you can see that it kind of maps out the Mechanim view, and you have these virtual buttons. So on click, you can move back, front, left, right, etc. But these also have key mapping. So when the keys are pressed, it emulates the click of a button. And on the other side is the camera feed. This is live. So as the driver is moving, they can also see their feed.
So this is our other UI for the other car. So we made it so that you from one UI you can control both cars. So the first thing we have over here is to control the camera and servo. One issue that we had was if we move it too quickly, like the camera would freeze. So we basically made it so that the user has to operate smooth turns. We have a ping feature, which is just a basic ping check. This is used for example, when you want to gauge general network connectivity. And yeah, we also have our camera feed on the right. So more on the camera feed. This is basically, we just integrated it. When we did this, a lot of times what would happen if it disconnected, basically it would fail to load. So we made like a retry button, and we also gave more error checking for the user to see.
And then lastly, we had a settings page. So this allowed the user to toggle on and off the safety mode and then also use keyboard shortcuts. This way, if anyone opens up this application, it's easy for them to learn on their own.
So after building these two vehicles, we wanted to test the maneuverability of each one, as well as gauge the driver's preferences on which features benefit or don't benefit the driving experience. So we created a course which consists of one right turn, or one left turn, one right turn, and then we also had each participant navigate under a chair right before they reached the finish line. And then we recorded the first and second try that each participant had for each vehicle, and we recorded the amount of time it took them to get to the finish line, as well as the number of collisions they had with other objects in the area. On average for both vehicles, the number of collisions went down by 0.1, but when we were tracking the average time to complete the course, we realized that the Ackerman vehicle had a greater decrease in the amount of time, which means that the learning rate was higher, and also means that technically it was easier to learn and to get adjusted to. And we hypothesized that that might be because it has a more standardized way of driving, because most normal cars, the front wheels rotate. But for the Mechanim vehicle, it might have been more new to some pilots.
So here's some of the future plans that we have. The first one is to improve the Mechanim movement and implement a joystick, because it was happening before it would be our users noted that it was very difficult to control the Mechanim car just with the keyboard. Another thing is more sensor integration. So we had already the distance sensor and the camera sensor, but we could further add depth sensing, audio feedback.
And then we also wanted to focus on better networking. We were noticing that we could definitely lower the latency, especially using a remote when we were remotely connecting. And we also were looking into using a cellular connection or like a hotspot and how that would work. So thank you. And then also a special thanks to Dr. Martin, Dr. Howard, Jenny, and Yvonne for making this possible. So any questions?